Now let's discuss vector operations, multiplication and division of a vector by a scalar. The product of vector A in boldface and scalar A yielding A is defined as a vector having a magnitude A. Now the sense of this vector A is the same as A, in that sense, provided A is a positive value. It is opposite to A if A is negative. In particular, the negative of a vector is formed by multiplying the vector by a scalar, such as the one shown in this. Vector A, and vector negative A. The negative of a vector is formed by multiplying it with a scalar -1. Now, division of a vector by a scalar can be defined using the laws of multiplication, since vector A divided by scalar A is equal to 1 over A times vector A. Of course, as long as A is not equal to 0. So, for example, if you have a vector A, then 2A would be twice as long, and negative, for example, 1.5A would be the opposite direction, since we multiplied by a scalar negative 1.5. And let's say 0.5A would be 0.5A. These are examples of such operations with vectors. Vector addition. Vectors can be added by using 3 methods. The parallelogram law is the first method, followed by the triangle construction methods. Now, 2 vectors A and B, such as force or position, may be added to form a resultant vector R, which is equal to A plus B. Now, all of these are in boldface. Using the parallelogram law. To do this, A and B are joined at their tails. So if we want to draw this graphically, let's try the first method, which is the parallelogram law, and join them at their tails. So suppose this is vector A, and this is vector B. Now, parallel lines are drawn from the head of each vector, and they intersect at a common point. So let's draw parallel lines. From each vector. And they intersect at a common point, thereby forming the adjacent sides of a parallelogram. If you have a look at this, it looks just like a parallelogram. The resultant R here that's R, which is equal to A plus B. R is the diagonal of the parallelogram, which extends from the tails of A and B to the intersection of the lines. That's the first method. We can also use B to A. We can also add B to A using a triangle construction. That's the second method. So the triangle construction says that we can add them by doing this. Now, The triangle construction is a special case of the parallelogram law, whereby vector B is added to vector A in a head-to-tail fashion by connecting the head of A to the tail of B. Now, the resultant R extends from the tail of A to the head of B. From the tail of A to the head of B. So this is R, which is equal to A plus B. Of course, all these vectors are in boldface to indicate that they are vectors. Now, by a similar manner, R can also be obtained by adding A to B. So we can call this form the parallelogram law. The second method is the triangle construction. Let's call it A. And the last one is another version of the triangle construction, but we can add A to B. So it is seen that vector addition is commutative. In other words, the vectors can be added in either order. So the resultant can also be R equals to A plus B, which is equal to B plus A. Let's make the other triangle construction by adding. You can draw the resultant R is equal to B plus A. Now, if you get confused by the signs, by the vector signs, now all of these are supposed to be in bold, but of course, this pen may not be very clear. So you can add simple arrows on top of each vector to indicate that they're vectors here. I think this would be a much better solution, and in order not to confuse yourself with any scalar quantities. Now, one last thing is to mention the commutative property, which is R equals to A plus B, which is equal to B plus A. Now, there's also a special case, which is if two vectors A and B are collinear, meaning they both have the same line of action. In this case, the parallelogram law reduces to an algebraic or scalar addition, R is equal to A plus B, since they both lie on the same line of action. So that would mean if you have, let's say, vector A over here and vector B, and they're both collinear, the resultant R would simply reduce to an algebraic or scalar addition, which means R is equal to A plus B. Vector subtraction. The resultant difference between two vectors A and B of the same type may be expressed as R prime equals to A minus B, which is equal to A plus negative B. And of course, you can put the little arrows on top of each. Now this prime is to indicate vector subtraction. The vector sum is shown graphically in this figure over here. Subtraction is therefore defined as a special case of addition, so the rules of vector addition also apply to vector subtraction. So if you have vectors A and B and you want to subtract them graphically by using the parallelogram law, you take negative B, which would be the opposite direction of B, and you join them together to draw the resultant R. Of course, you draw the parallel lines, and that would form the intersection, and you would draw the resultant from the tails of those two vectors to form R prime. Of course, the similar way of triangle construction can also be used, where you add negative B to A, and you form the resultant R prime from the tail of A to the head of vector negative B. Resolution of vector. A vector may be resolved into two components having known lines of action by using the parallelogram law. For example, if R, if vector R in this figure, is to be resolved into components acting along the lines of A and B, one starts at the head of R and extends a line parallel to A until it intersects B. Likewise, a line parallel to B is drawn from the head of R to the point of intersection with A. Now, the two components, A and B, are then drawn such that they extend from the tail of R to the points of intersection. We call these components of vector of the resultant R. This concept is very important since it will be used extensively in statics example problems.